Hello class, this is CSE-4600 section 62. This is supposed to be your week 4 video, but I'm gonna put it under week 5 content, just to be consistent. And that's because I guess this week is gonna have 2 videos then. So for the sake of consistency, I'm just gonna say this is your week 5 video even though it's a week 4 content. Okay, so this is a continuation of the lab instructions video. So the lab instruction video, I did a sort of preview into what this part of the chapter is gonna entail. We're gonna be talking about threads more in depth. Yeah, we have a threading library, but what does it do, like, under the hood? And then we're gonna look into some of the complications that we encounter by having multiple things running at once as part of the same program. Alright, so we're gonna begin with pthreads. So this is the pthreads library that most Unix systems will support. So most Unix systems support pthreads. There is a way to install it on... There is a Windows implementation of the pthreads standard, but you need to... It's quite a process just to install it on Windows. So you can do part 1B of the lab. You can do part B of the lab on a Windows computer if you go through the process of installing it on a Windows system. But for the sake of consistency, if you already have a virtual machine, and by the way, I found instructions on how you can set up your own VM online that I've just simply posted onto a canvas. You can look into that. There's a million tutorials online, but I would recommend whichever one is most up to date because software changes all the time, you know? Anyway, the pthreads library is how we can make multi-threaded programs. So, as I said in the last video, we're really dealing with a handful of thread calls. Pthread create creates a new thread. Pthread exit terminates the calling thread. Pthread join. Fork and wait model says that we have one main thread that forks a bunch of other threads. Those threads do a bunch of different things, and then after some time they're gonna finish the job and they'll join back with the main thread. All pthreads have a set of properties, an identifier, a set of registers, and a set of attributes that's stored in a data structure that includes the stack size, scheduling parameters, and whatever information is needed to create a thread. We create a thread using pthread create. It's analogous to the fork system call, but we don't have an accompanying exec call. Because when we create a thread, it is sharing whatever program belongs to that one process. So we don't have an exec call to wipe whatever is in memory and replace it with something else. And of course we have pthread exit, that is like wait with processes. Sometimes a thread must finish. Sometimes a thread must wait for another thread to finish its work and finish executing. That's pthread join. And as mentioned yesterday, there are no built-in mechanisms to signal when threads should be swapped out for other threads because that exists at the process level, not at the thread level, so we need functions to do that ourselves, and that one is called pthread yield. Each pthread has attributes associated with it, and we create those using pthread attribute init, and pthread attribute destroy destroys those attributes. We're not really playing with that all that much when we try out our Hello World lab, by the way. But yeah, those are the six functions that are described in the textbook on how we can create, use, and destroy threads. And here's that example Hello World program. You can try that out, or you can try this one out. It just says Hello World, but then it creates 10 threads that also say Hello World. So when we create these threads, where are they going? Well, there are two ways to implement threads in the operating system, and they can either be at the user space or at the kernel space. There are also advantages and disadvantages to both of these implementations, so there is a sort of third hybrid implementation. So let's look at what happens if we try to make threads in the user space. So in this implementation, the kernel has no idea that there are multiple threads. As far as the kernel is concerned, it's just managing ordinary single-threaded processes. So this has the advantage of supporting threads on an operating system that doesn't support threads. At one point, all operating systems were like this, so we needed a library to implement our threads. And each process can have its own customized scheduling algorithm. More on that later. So threads are run on top of a runtime system, which is a collection of thread-related procedures. So these are the functions that we would call to create and terminate threads, wait for threads, and so on. When threads are managed in user space, each process needs a thread table. You know how the process has a process table, and it uses that table to keep track of what processes are running? The process needs a similar table to keep track of which threads are running. Or rather, it's used to keep track of the per-thread properties. Also, much like how the process table keeps track of the per-process properties. If a thread is moved from the ready state to the block state, we need to store that information in the table. Or rather, we have to update that information in the table, because there's going to be entries for each thread that is updated based on whatever happens to each thread. So a thread could be running, and then we need to block the thread because we need some other thread to run. When a thread does something that causes it to be blocked locally, say it's waiting for another thread to finish something, it calls a runtime system procedure that checks which threads must be put in a blocked state. If there are threads to be blocked, it stores that blocked threads registers into the thread table, and then it looks for another thread that's ready to run, and then it reloads that thread's registers from the table. So the process in which the means of how a process is switched for another process is called a context switch. When we do a context switch at the level of processes, we need to save everything that the program was doing. That includes the registers, that includes the stack, and all that. But we also need to save we need to save the state of what memory it had. So we need to save all of that, and then we can take that process out and then switch in a different process. When it comes to context switching threads, because the threads of one that belong to one process are all sharing memory, we don't have to context switch memory anymore. That's what makes context switching threads much more lightweight compared to context switching processes. So there's one key difference between processes and threads. When a thread is finished running and calls thread yield, that thread's information is saved in the thread table. The thread schedule is then called to select another process to run. With processes, and I guess this is another key thing about processes as well. When we need to context switch processes, with processes, a trap is to the OS is needed to signal that a context switch should be carried out. However, with threads, we don't need to call the OS anymore. That's the other thing that makes it so lightweight. That's the thing that makes context switching threads so much more lightweight than it is with context switching processes. We have to call the OS for that. But with context switching threads, we just need to do a local procedure call. That is it. So the operating system does not need to get involved here, which speeds up the process, which speeds up context switching threads that are a part of the same process. So there are some problems with this. Yeah, so there are some problems with context switching. Well, it's not that the problem is with context switching threads. Well, it actually kind of is. So here's a problem with implementing threads in the user space. When we have a system call, how are blocking system calls implemented? Say a thread is performing a blocking system call. Say it's calling read for keyboard input. What happens is it blocks all other threads in the process. So one way we can solve this is to have non-blocking system calls, but that will require changes to the operating system itself, which might not be the most elegant solution, or maybe it's something we might not be able to do at all. There is one alternative solution to that. It's to check in advance whether a call will block. So this exists in most Unix systems as the select system call. It allows the caller to tell whether a read system call will block. So in the case of reading from keyboard input, we check select to determine whether calling read would block. If the call will block, the call is not made and another thread is run. The next time the runtime system gets control, it checks again whether it's safe to call read again. This, however, requires rewrites to the system call library. Also, what happens when we get a page fault? Now, we didn't get to page faults yet. That's already chapter 3. But basically, paging and page faults, that's chapter 3. But paging is a means of running a program without having the whole program loaded into memory. This is done by dividing up the program into what are called pages. So this way, we can load a program, but we don't need to load all the stuff that we don't need to use right away. The problem with paging is this. If we don't have a page that we need and we try to access it, it results in what's called a page fault. This blocks the process, and then the OS must fetch the page from something like secondary storage and then load that into memory. If a thread causes a page fault, it might block all other threads, even though those other threads might still be able to run. So here's an analogy about that. So I talked about the train set analogy in the previous lab video. Basically, it's this. Imagine you are building a Lego train set. A process is the step-by-step action of building the train, brick by brick, car by car. And you might have other accessories as well. You might have a train station, you might have non-train vehicles. If this is a freight train, you might have some device that would move storage containers on and off the train. You can build the train yourself, but let's imagine this is a really big train set. Or it's like multiple train sets that you're trying to combine into one. You can build it yourself, but it's gonna go much faster if you have some helping hands. Multi-threading is where you have your friends help out by each building a different train car. So you and your friends are different threads because you and your friends are executing different instructions to build different parts of your train. And the reason why we can do this is this. When we build this train, it does not matter in which the order we build these trains. So we can just build the locomotive first, or we can build the boxcar first, or we can build the caboose first. Doesn't matter. What matters is we can build these train cars in any order we want, which in theory means we can build these train cars at the same time. So, what is paging in this analogy? So, as you build this big train, you might have a big pile of instruction manuals. Paging is where we have the instruction manuals, but we don't have room for all of them, so you have to move them off the table. If we need to build a specific train car, and there's a separate instruction booklet to build the boxcar, there's a separate instruction booklet to build the tanker car, there's a separate instruction booklet to build the caboose. Paging is where you only just have the instruction manuals you need. And a page fault is you just moved off the table the instruction manual you need, and you have to go find it. Ideally, when you have this page fault, it shouldn't stop everyone from what they're doing, just so you can find that one manual. Unless you really lost it. So, as I said, a page fault is like trying to find a manual you had moved off the table because you didn't have room for it. And ideally, it shouldn't stop everyone else from building their train cars just so you can find the manual you need to build your train car. So that's what a page fault is in this multi-threading analogy. So, that is how we implement threads in the user space. There is another implementation that involves making threads in the kernel space. In this implementation, we don't need a runtime system. And there isn't a thread table in each process. Rather, it's the kernel that's managing both processes and threads. When a thread wants to create a new thread or destroy an existing thread, it makes a kernel call, and then the kernel is the one that makes the new thread, and then it updates the thread table accordingly. So the thread table in the kernel holds each thread's register state. The thread table in the kernel holds each thread's registers, state, and other info, much like how it keeps track of each process using the process table. Oh, and as I said, the kernel now has both a process table and a thread table. All calls that might block a thread, these are all implemented as system calls. This, however, comes at a higher cost to having a runtime system procedure. When a thread blocks, the thread can either run a different thread from the same process or a different thread from a different process, depending on what's ready to run. With user-level threads, the runtime system keeps running threads within one process until the kernel takes away the CPU from it, or there are no more threads to run. So here's the one hiccup with kernel space threads. Because it's so expensive, because of the high cost of creating and destroying threads, some systems recycle threads. So in many video games, there is a concept called object pooling. Say you have 1,000 cubes that you want to have as part of your video game as particles or props or whatever. You could create and destroy them as needed, but that is an expensive process. So instead, the video game maintains what's called an object pool of, say, 1,000 cubes, and it takes objects in and out of the pool as needed. If we want to create a cube that we want to put in a video game as part of a particle effect or something like that, or maybe not cubes, but rather, say, a goblin as part of a goblin army. We don't need to create and destroy a new goblin each time. Rather, we have a pool of 1,000 goblins, and every time we need a goblin, we just take one out of the pool, activate him, and now we have a goblin in our video game. When that goblin is killed as a result of combat, instead of destroying that goblin and freeing him up from memory, the goblin is put back into the pool in a idle state. And much of this applies to threads here. So there would be some sort of thread pool that the kernel manages. It's full of threads that the kernel can use. So instead of creating and destroying threads, threads are reused. When a process wants to create a thread, the kernel just takes one of these threads from the pool, and boom, we have a new thread. What this does is it saves the system the overhead of creating and destroying threads, much like how object pooling saves the overhead of creating and destroying game objects. Kernel threads don't require any new non-blocking system calls. If a thread causes a page fault, the kernel checks whether there are any more runnable threads as part of that process. If so, one of those threads is run as the page is being paged in. So remember what I said about paging and page faults? When a program tries to read something that isn't loaded into memory yet, that causes a page fault. That should not cause all other threads to stop what they're doing. So what the kernel can do is it's going to decide, okay, thread 1 caused a page fault, so I guess thread 1's blocked. Thread 2, you can run in the meantime while I go fetch page 1's missing page. The only issue here is that the system call itself, that also has a high cost. So what having threads at the kernel level does is it solves a lot of the problems that it had with having user level threads, but not all of them. For example, what happens when a multi-threaded process forks? Does the forked process get only one thread, or does it get as many threads as the calling process? What's the answer to that? Well, it depends. If the fork process calls exec, then it really only should have one thread. Because when we have processes, there's always one thread of execution. At least until it starts making multiple threads. If the fork process continues to execute, it might be better to have as many threads as the original program. So it may be better to reproduce all the threads from the original. There's also the issue of signals. In the classical process model, signals are sent to threads. If there are multiple threads, who gets the signal? So really, this depends on whether there's one thread to handle the signal or there are multiple threads to handle the signal. And because of this, there have been many ways to try to get a hybrid implementation. So this is what it looks like. Here's one way it could look like. So instead of either implementation, here we have one kernel thread and it's multiplexed onto multiple user threads. So the programmer can determine how many kernel threads to use and how many user level threads to map to each one. So we can have a 5-thread program, but really it uses 2 kernel threads. That's under the assumption that we don't need that many threads to be running at the same time. So here's what it looks. So here's some more detail. So the kernel is only aware of the kernel level threads. And if we have multiple user threads mapped onto one kernel thread, they basically take turns using that kernel thread. So as far as the kernel is concerned, we only have, in this example, 2 threads, even though in the process there are 5 threads. This way we don't have to this way we don't have to make as many threads compared to... Okay, basically this makes it so the kernel doesn't have to make as many threads as there are threads in the process. So let's look at the next topic here, and that is scheduler activations. It turns out that kernel threads are better than user-level threads, but they're still slower, so researchers have tried to find ways to improve upon that, and one of them, devised by several researchers, Anderson Anderson et al. In 1992, Edler et al. In 1998, and Scott et al. 1990. They basically, this is what scheduler activations is. So this is a way of trying to get the best of both worlds of user level threads and kernel level threads. So the goal is to mimic the functionality of kernel threads, but with the flexibility and performance that user level threads has. User threads shouldn't have to make non-blocking system calls or check whether a system call results in a block. If a thread blocks, it shouldn't block any other threads. And even if it did, there should be another thread that's ready to run so that so even if a thread is blocked, some other thread can still run. Efficiency is achieved by avoiding unnecessary transitions between user and kernel space. If a thread blocks waiting for another thread to do something, there should be no reason to invoke the kernel. If we don't invoke the kernel, we don't have the overhead of doing so. This saves on overhead, this increases performance. The user space runtime system can block the synchronizing thread, and then it'll schedule a new thread by itself. When scheduler activations are used, the kernel assigns a certain number of virtual processors to each thread, and then it lets the user space runtime system allocate these threads to processes. This also applies to a multi-core CPU. So initially, one process only has one virtual CPU allocated to it, but the process can request for more if needed and return them when they're no longer needed. But the kernel can also take virtual CPUs away if it needs to give them to a process that needs it way more. Say there's a process that's been waiting too long and it really needs the processor core available so it can do something. When the kernel knows a thread has blocked, the kernel notifies the process's runtime system by passing to the stack the number of the thread and a description of the event that had happened. This notification happens by having the kernel activate the runtime system at a known address, and this is called an upcall. Once activated, the runtime system can reschedule threads. This typically happens by marking the current thread as blocked and restarting another thread that's ready to run from a list of ready threads. When the kernel learns that the original thread is ready to run again, it makes another upcall, so that thread can either run again, or maybe it's put into a list of threads to run later because, well, there might be some other thread that's also ready to run. When a hardware interrupt occurs while a user thread is running, the interrupted CPU switches to kernel mode. If the process isn't interested in the interrupt, it puts the interrupted thread back to the state that it was right before the interrupt. If the process is interested in the interrupt, then the interrupted thread is suspended. The runtime system is started on the virtual CPU with the state of the interrupted thread on the stack. What thread to run next is then up to the runtime system to decide. So it could run the interrupted thread again, or something else, or it could do something else. So there is one objection to schedule activations, and it is this. In a layered system, in a layered system, a layer offers services to the next layer, but it cannot call any procedures in the next layer. So the problem with upcalls is it violates this layer structure. Upcalls don't do that. Upcalls don't obey the rules set forth by a layered system. So that's the one objection to schedule activations. So here is an application of threads that you might see on a distributed network. So a distributed network is basically a bunch of computers linked together by a network. In a distributed system, we have messages being sent back and forth between computers. So, processes are sending messages to other processes, and they might be going to a process on a different computer, or might be going to a process on the same computer. Doesn't matter. We're sending messages between processes, and those processes need some means of handling incoming messages, and it's usually like this. We have a process that is blocked on a receive system call waiting for a message. So this thread calls receive, and it's blocked because there's nothing to receive. So it's waiting for something to come in, it's waiting for something to come in. It's much like if you're just sitting at your doorstep waiting for your Amazon package to arrive. When a message arrives, the process accepts it. Let me back up. When a message arrives, the process accepts the message, it unpacks it, it examines the contents, and then it starts to process the message. So a different system is also possible to handle incoming threads, and it is this. It's called a pop-up thread. So instead of having a process handle incoming messages, when there's an incoming message, we just create a new thread. Since this is a newly created thread, it doesn't have a previous state. It doesn't have registers. It does, but they weren't loaded with anything before. It doesn't have any previous whatever that we need to restore. This speeds up making the thread and reduces the latency between message arrival and processing of that message. So we create a whole new thread, and then that thread handles the message. This, however, requires some advanced planning. In which process is the thread run? Also, if the pop-up thread is a kernel space thread, then making the thread becomes much faster compared to making a user space thread. However, there is a danger. If the kernel is buggy, there's no way to preempt it, and the message may be permanently lost. Okay, so section 2.2.9 is a few paragraphs on how to make single-threaded code multi-threaded. So there are some concerns with turning a single-threaded program into a multi-threaded program. Namely, how to deal with global variables, how to deal with library procedures with non-reentrant code. How does a library handle a second procedure call when it's not done with the first? How to deal with the memory allocation. How to handle signals that are not thread-specific, and how to manage the stack. So those are some of the concerns and pitfalls with making single-threaded code multi-threaded. You can read that on your own, but for now I would like to continue on with something called inter-process communication. So we kind of looked at that already. When you have a distributed system that is a network of connected computers, processes may send other things to other processes. Though, as far as the process is concerned, it thinks it has the whole computer to itself. It thinks it has the whole computer's worth of resources to itself, even though there's only one computer's worth of resources to go around. However, it is quite often for processes to communicate with one another, and that is called inter-process communication. That's where, for example, processes send messages to other processes, possibly to another process on a different computer. There are, however, 3 issues regarding IPC. How to pass information between processes, making sure processes don't get in each other's way, and making sure operations are done in the correct order. So, IPC is for both processes and threads. So any solutions that we talk about for IPC here, they apply to both processes and threads, with one exception. If we have multiple threads as part of one process, they don't have a problem passing information between one another because they all share memory. There's gonna be some space of memory that all threads are able to access. So any means of communication between threads, that's basically a given because of the nature of sharing memory between threads. Just keep in mind that any solution that we present here will apply to both processes and threads. So now we get into a problem that can manifest as part of having multiple processes work together. So this is something that'll happen when we have processes trying to work together. Consider the simple example of a print spooler. So when a process wants to print a file, it enters the file name into what's called a spooler directory. Meanwhile, a printer daemon periodically checks for any files to be printed. If it finds a file, it prints that file, and then it removes it from the spooler directory. So let's say we have a spooler directory and it's full of files, but we also have two variables. The first one, called in, points to the next available slot in the spooler directory. And out points to the next file to be printed. We're more interested in the in variable because that's the one that's pointing to the next available open slot. Meanwhile, we have two processes coming in with files to print of their own. Process A reads the value of the in variable and stores it into its own local variable. Right before it writes its file into slot number 7, it's interrupted, and process B runs next. It reads in and stores the value of in into its own local variable. So process A and B have their own local variables that stored the value of in. So you would think that process A is never going to have a file. You would think that process A got interrupted, so it's process A that is unable to print its file. However, that's not the case, because race conditions are a little bit weird. So process A got interrupted in the process. Process A got interrupted while trying to write its file into slot number 7. Right, it got interrupted while trying to write its file name into slot 7. Process B writes its file name into slot 7. And then process B changes the value of in to be 7 plus 1. Eventually, process A starts running again. But it has in its local variable the in value of what it was before process B had changed it. So it's still holding a 7 in its own local variable. So process A thinks that the next available slot is slot number 7, even though it's slot number 8. Process A never got that updated value. So it thinks that the next available slot is slot number 7. So it's gonna write its file name into slot number 7. But process B had already written something in slot 7. So now, whatever process B had wrote into slot 7, it's now gone because process A had overwritten it. So when the printer daemon comes in to print out files, it's gonna print out process A's document, but it's never gonna print out process B's document because it got overwritten. This is an example of a race condition, and trying to debug a race condition it's not fun. And the reason why we need to know this is simply because, well, we have hardware nowadays that is, well, fairly cheap than it was like a decade ago, where we have high core count CPUs just rarely available. Like, the Ryzen 7 is a $300 whatever CPU. That is an 8-core CPU. And now we have the Ryzen 9, which you might be able to fetch for as low as $500. That's a 16-core 32-thread CPU. You know that song where someone tried to get an edgy 13 tattoo, but the tattoo parlor screwed up and they drew a 31 instead? Maybe it's through race conditions that screw up happened. Yes, for a 13, but through the magic of race conditions, they drew a 31. So, it's called race conditions because we have two processes trying to race one another, trying to write something into a shared memory slot before some other process can overwrite it. But the thing about a race condition is this. This is a weird race in which you have, say, multiple processes racing one another, trying to get something written into a slot of memory. And everyone must participate in this race. Whoever gets there first is going to be the first to be overwritten. And whoever arrives last, that is the value that's going to be saved. In a race condition, last place wins. So how do we avoid this? Well, the key thing to know about race conditions is that they happen when processes share resources. So all we need to do is we need a mechanism that will prevent processes from accessing something another process is already accessing. We need a means of enforcing mutual exclusion. So with the spooling example from earlier, what had happened was, process A was in the middle of doing something with the spooler directory. So process B should not have preempted process A. Rather, what should have happened is process B should have been blocked and then unblocked when process A was done with its work in the spooler directory. Part of the time, a process does things that don't lead to race conditions. It's only when we try to access that shared resource, that spooler directory, for example, that we have the danger of race conditions. When a program executes code that requires access to a shared resource, that part of the program is called a critical section. The textbook calls it critical region, but I know it as a critical section. So, enforcing mutual exclusions on the level of the critical section, that ensures that only one program, or only one process, is allowed in a shared resource. If we enforce mutual exclusion at that level, we avoid race conditions. However, that mutual exclusion alone isn't enough to... Hold on. However, mutual exclusion at the level of critical sections, that alone isn't enough to make sure we don't... That alone isn't enough to ensure we have efficient use of resources. So we actually need 4 conditions. And the first one we've already seen. Mutual exclusion. No two processes may be simultaneously inside their critical sections. That's number 1. Number 2. No assumptions can be made about CPU speeds or CPU core counts. Number 3. No process outside its critical section can block another process. And number 4. No process should have to wait forever to enter its critical section. Let's go back to that spooler directory example. So let me just get my webcam in the right place, and there we go. So in that spooler directory, we have process A entered the critical section because it's accessing the spooler directory. Process B, while process A is doing something with the spooler directory, it's writing its file into the directory, process B also wants to enter the spooler directory, so it tries to enter its critical section. However, because process A is already there, process B is going to be blocked. So process B is blocked. It can't do anything. Not until process A leaves the critical section. When that happens, process B is now allowed to enter its critical section. At that point, the values in the spooler directory's variables, because the first available slot was 7, if process A was allowed to do its thing without interruption, it will update that value to 8. If we have mutual exclusion, process A will do its thing and update that value to 8. Now, process B is allowed to enter, and it sees, well, that the next available slot is 8 because process A had already changed it to the correct value. So now, if we have mutual exclusion in here, it means both processes are able to print their files. Unless the printer daemon crashes. Anyway. So, mutual exclusion with something called busy waiting. So, how do we enforce mutual exclusion? Well, on a single processor system, the simple solution is to have each process disable all interrupts right after it enters the critical section and then re-enables them right before it leaves. No, just right after it leaves, I should say. This way, processes can read and update shared information without any other processes intervening or interfering. Though this is an unattractive solution because it gives user processes the ability to turn off interrupts. What happens if a process forgets to turn them back on? Also, what happens on a multi-core CPU? If we disable interrupts, it only disables them on that one CPU core. Other processes that are running on other CPU cores are still able to run. So whatever it is that's happening with that one process that turned off interrupts, it's not going to affect any other processes that are running on other CPUs. On the other hand, it's frequently convenient for the kernel to disable interrupts when it's updating, say, the list of ready processes. That cannot be interrupted. The point is this. As useful as disabling interrupts is, it's not an appropriate solution for enforcing mutual exclusion. So we don't want to disable interrupts. Rather, we don't want to give user processes this much power because it might break the whole system. But let's try a different solution. It's called a lock variable. Consider a single shared lock variable. It's initially set to 0. When a process wants to enter its critical section, it tests the lock. If it's 0, the process sets the lock to 1, and then it enters its critical section. If the lock was already 1, the process simply waits until it becomes 0. This, however, has the same problem as the spooler directory from earlier. A process reads the lock and it was 0. Before the process can set it to 0, another process is scheduled to run. That process sees the lock is 0 and it proceeds to enter its critical section. When the first process runs again, it will set that lock to run. It doesn't check it. And now we have two processes in their critical sections. Not good. So let's try a different solution. Assuming the operating system was written in C or C++, which is usually the case, two processes can simply alternate between their critical sections by having these infinite loops. So there is a variable called turn, and it's initially set to 0. This keeps track of which process is allowed to run in its critical section. Process 0 inspects this variable. So let's just say this variable turn is set to 0. Process 0 executes this infinite loop, while turn is not 0. Loop. and it's going to keep looping until it is set to... No, while turn is not 0. It's going to loop forever until that turn value is set to 0. However, since it was already 0, process 0 just skips this whole infinite loop here, and it goes into executing its critical section. Right after it leaves, it sets the turn variable to 1. At that point, it's now process 1's turn to run. So process 0 was doing stuff in its critical section. But let's say, for example, process 1 wanted to enter its critical section, but it's not process 1's turn to run. So what will happen? So this turn variable is at 0. This turn variable is set to 0. Process 1 tries to enter its critical section. So now, before it can enter its critical section here, it's gonna do this while loop here. So while turn is not 1, loop. And it's gonna keep, and now it's gonna loop until process 0 leaves and sets that turn value from 0 to 1. So this is what's known as a busy waiting, because process 1 is in this infinite loop of checking whether that turn variable was ever set to 1. And it's gonna keep looping until process 0 changes that turn value from 0 to 1. So this is how we have two processes alternate between their critical sections. This has a problem, and it's this. It wastes valuable CPU time. We would only want to use a busy waiting if the wait is reasonably short. So the problem with busy waiting here is that the CPU is doing work, but it's not doing productive work. You can just imagine the process is just twiddling their thumbs, or say playing with a spring-based door stopper. They're doing work, but it's not useful work. So it's wasting valuable CPU time. So this implementation here is what's known as a spin lock. Also, this implementation violates the third condition of avoiding race conditions. No process should block another process if it's not in a critical section. Now we're gonna get into another solution here. This was created by someone named Peterson. And hold on. Okay, so I guess there's a missing slide in here, but basically Peterson's solution is a scalable means of it's a scaled up version of our busy waiting from earlier. So it works like this. So here's the thing. We define two functions for entering the critical section and then leaving the critical section. When those functions are called, the calling process passes in its process ID. So the solution here for achieving mutual exclusion, this is scalable to any number of processes. But we're going to show it with two here because that's a simple example. So we have a variable called turn that says, whose turn is it? And we have a variable array called interested. This is an array that's initially set to all zeros, indicating that no one's interested in entering their critical sections. So before entering its critical section, each process calls enter region and it passes in its process ID. So a process ID in this context, simply, it's not the process ID assigned by the operating system, rather it's a process ID that is assigned by, say, the programmer, that is used as a convenient means of identifying which process is which. So we have process 0 and process 1 in this example, not going by the process IDs that the OS would give to these processes. So we have process 0 and process 1. in this example. So, regardless, either process must call enter region and pass in its process ID. When these processes leave, they must call leave region and then pass in its process ID. The turn variable indicates whose turn is it, and the array of interested, that's an array of booleans indicating which processes are interested in entering their critical sections, and these booleans are all initially set to false. And again, this applies to this works for any number of processes, but in this example, it's just only showing 2 processes. Initially, neither process is in its critical section, and no processes are interested in entering them. But let's just say process 0 is interested in executing its critical section, so it calls enter region. Let's look at the code here. Since process 1 is interested at the moment, when it calls enter region, what happens is this. Look at this code. Basically, it's much like the busy waiting from before. Basically, this whole thing, this enter region function, it returns right away because there are no other processes interested in running their critical sections. So process 0 can enter its critical section right away. Suppose now that process 1 wishes to enter its critical section, while process 0 is already in its critical section. When process 1 calls enter region, it will hang until interested 0 becomes false, because when process 1 called enter region, it basically showed its interest in entering its critical section. So now this array of interested processes, now interested 0 is true, and it won't go back to false until process 0 calls leave region. So when process calls enter region, it will hang until process 0 leaves. When process 0 leaves, it's gonna call leave region and say, I'm no longer interested in executing my critical section. That indicates to process 2 that it's now process 2's turn to run. Now consider what happens when both processes try to enter their critical sections at the same time. Both function calls will happen at the same time. So process 1 calls enter region, and process 2 also calls enter region. Both function calls will store their process IDs in the variable turn. However, the tiebreaker is whoever wrote that variable to that variable last, because in a race condition, last place wins. So that is the tiebreaker for how we get more than one. This is the tiebreaker when more than one process shows interest in running its critical section. So that is Peterson's solution to the mutual exclusion problem. Now let's look at a hardware solution. So some CPUs have a special instruction that we can use for enforcing mutual exclusion. That instruction is called TSL. So it tests and sets a lock. It reads the contents of the memory word lock into register RX, and then it stores a non-zero value at that memory address lock. So this operation is guaranteed to be done start to finish without interruption. This is what's called an atomic operation, by the way. Atomic, in the original sense of the Greek word atomos, meaning uncuttable. We cannot cut it up into anything smaller. That's why we called atoms atoms, because we cannot cut them up into anything smaller. Well, we can cut them up into smaller things, but if you cut up, say, a uranium nucleus into smaller pieces, then it stops being a uranium nucleus. It starts being a nuclear fireball. But I guess that depends on how many neutrons were ejected in the process. Anyway, if we have an operation that cannot be subdivided into anything smaller, it's called an atomic operation. And this TSL operation is an example of an atomic operation. It cannot be interrupted, it cannot be cut up into smaller pieces, it must be done from start to finish. So what happens here? When we do this TSL instruction, the CPU executing this instruction locks the memory bus to prohibit other CPUs from accessing memory until it's done. So this is a process this is an instruction whose steps cannot be interrupted by anything, because it locks the memory bus to keep all other processes from accessing memory. Note that locking the memory bus is different from disabling interrupts. So, disabling interrupts followed by performing a memory read and write doesn't keep other CPUs from accessing memory in between the read and the write. And more to the point, disabling interrupts only affects the CPU core that had disabled interrupts. It does not affect any other CPUs. Locking the memory bus ensures that no other CPU cores can make changes to memory until the core that had locked the bus is done. So using the TSL instruction requires a shared variable lock to coordinate access to shared memory. When lock is 0, any process may set it to 1 using the TSL instruction. If a process wishes to do something to shared memory, the TSL instruction is called first. The variable lock is set to 1, and the process reads and or writes to shared memory. When the process is done, the process sets lock back to 0 using a move instruction. And the code for that, the assembly code for that, might look something like this. So the first instruction in this inter-region subroutine here, in this inter-region procedure here, the first instruction in there copies the old value of lock to a register, and then it sets that lock to 1. And in the second instruction, that old value is compared with the 0. If that value of that register was not equal to 0, then it's just gonna jump to the beginning of inter-region and do it all again. It's gonna read the value from lock and store it into a register. And then it's going to compare that register with the number 0. And if it's still not equal, it's gonna go back to the beginning of inter-region and do it all over again. And if it's not equal, then it's gonna do it all over again. And if it's not equal, it's gonna do it all over again. It basically forces the programming into an infinite loop, where it's doing nothing but checking whether it's its turn to enter its critical section. If some other process is in its critical section, when it leaves, it's gonna move the number 0 into the lock register. No, it's gonna not register. It's gonna move the value 0 into the word lock, and then it's gonna return. For a process that was stuck in this infinite loop waiting for its turn, it's going to copy the value in the word lock into a register, and then it's gonna compare it to the number 0. In this case, it is 0. So now, it's not gonna jump back to the beginning anymore. Rather, it's going to return. So now, the process that had called inter-region is now able to enter its critical section. So this makes it easy to solve the critical section problem. However, this assumes that processes call enter region and leave region in the correct order, and they call it at all. Because if we forget to call one of these things, we break the whole system. There's an alternative to TSL, and that's the exchange operation. All Intel x86 CPUs have this operation for low-level synchronization. It does much the same thing as TSL. So the thing about Peterson's solution and those using TSL and exchange, These are correct. They do enforce mutual exclusion, but they come at a cost. They require a busy waiting. When a process tries to enter its critical section and it can't, the process performs an infinite loop until it can. This wastes valuable CPU time. These processes are doing work, but they're not doing productive work. And we want to keep the CPU busy, but we don't want to keep the CPU busy with like stuff that isn't productive to doing work. So to prevent CPU time being wasted, instead of having these processes that are waiting be caught in an infinite loop of doing unproductive work, what we could do instead is have these processes go to sleep. So the process goes to sleep, and whichever process was executing its critical section, now it has the task of waking up these processes that fell asleep because they were waiting for their turn on the critical section. Basically, these processes suspend themselves. So they basically suspend themselves to pass the time needed to wait for their turn on the accessing this shared resource. And again, this requires that any processes that are done executing their critical sections, they need to wake up that process. So, yeah, that's basically the last slide in this presentation. We're gonna discuss this even further. We're still not done with chapter 2, by the way. There is still a lot of content in there. So far we talked about processes, what is a process, what is a thread, and what happens when we have multiple processes and or threads doing things on the CPU. Remember, ultimately we want to keep the CPU busy, but we don't want to keep it busy with stuff that is inconducive to doing work. So, if we introduce sleep and wake up, now these processes that are blocked from accessing a critical section, instead of doing unproductive work, they go to sleep. So we're going to look at a few solutions to that in the next set of slides. So for now, I would like you to work on the two labs, the two parts of the lab 1A and 1B. They're both Hello World programs. One uses processes, the other uses threads. So with that, I'm going to leave it there for now. And if you have any questions on anything, definitely email me about it and I'll answer as soon as possible. So with that, we're going to stop here and then we're going to look at part 3 of chapter 2, hopefully in the next week. Alright, take care.